So I'm going to discuss another example of a family of transfer functions to check whether this family of transfer functions is actually obeying the three rules that we laid out in the previous module. And we're going to take the familiar example of constant propagation for a single variable x. And recall that the semi-lattice formed for this particular data flow analysis was consisting of these values top and bottom. Top was basically representing the unreachable value, or the program point hasn't been reached so far. Then all these constant values, which represent all the possible constants that this variable x can take, assuming x is an integer variable, then maybe it can take all these integer values. And then bottom basically says that we cannot be sure that it is a constant, and so it may not be a constant, and that's what bottom means. And now if we look at all the transfer functions that we discussed, one of the transfer functions was that if the program involves a statement which assigns a constant to the variable x, then the transfer function was defined as follows: that given an input value in, the output value should be less than equal to, if we are basically modeling this as a set of constraints, or equal to if we are modeling this as an algorithm. Then if in equals top, which means if in is not reachable, then even out is not reachable, else it is just constant, because we know that x is equal to c is going to always produce a constant in the variable x. And so the transfer function says that if in is top, then out is also top, otherwise out is c. Now this is one transfer function. Similarly, there was another transfer function which was for another statement where we are not assigning x to a constant c, but some arbitrary expression, which I am denoting with this dot dot dot. And in this case, the transfer function looks like the one shown here, which I'm labeling as the second transfer function. The first one as I'm calling it the first transfer function. So it says if in equals top, then top, just like the first transfer function, else bottom, because we are assigning some arbitrary expression to x. We can't be sure that arbitrary expression is going to be a constant or not. So conservatively, we just assign the value bottom. And this forms our second transfer function in the family of transfer functions for this particular data flow analysis of constant propagation on a single variable. Finally, there was this transfer function which did not involve x, did not write to x at all. So for example, if there's a statement which just assigns to another variable y, or if there was a branch statement or something like that, then the out value is just a copy of the in value, or the transfer function is just the identity function, or fn equals in. And so this forms our third transfer function. And we could potentially make the transfer functions more sophisticated, but let's assume that these are the only three transfer functions available, and these actually suffice for, although they may not give the most precise answer, but they actually, we have covered all the possible cases that a program statement may be in a 3-address code IR program. And so these are the three transfer functions that we have discussed. The first one says, I'm using this ternary operation, this ternary operator question mark and colon, as it is used in the C language, for example. So if x equals top, then top, otherwise C. Another transfer function was if x equals top, then top, otherwise bottom. And the third transfer function was the identity function, which is fx equals x, which was if we are not writing to x at all. Okay, so these are the three transfer functions, and I want to check whether it satisfies these three. This set of functions satisfies the rules for it to be a family of functions usable in a data flow analysis. And the first property was that for all the transfer functions belonging to this family, which is this family of three functions, is it true that all the functions map the same domain of values, take a value from the domain of values and return a value again in the domain of values? So it's easy to see that, because the domain of values is either top, bottom, or one of the constants, and the values that are being returned by each of these functions are also one of either top, bottom, or one of the constants. So it's very easy to see that all the three functions actually satisfy the first requirement. If I look at the second requirement, it says that the ID function, the identity function, should belong to the family of transfer functions f. And that's also true because the third function is indeed the identity function, it just returns the input value. So that's also easy to check. Now let's look at the third one, which is slightly more complex. It says that for all f comma g belonging to capital F, is it true that the composition of f and g also belongs to capital F? Now we have three different transfer functions in this family. So the possible number of compositions that I can create are, I can have 3 values for f, so that's 3. And then I can have 3 values, 3 different possible values for g. So 3 cross 3, 9. So, I need to check 9 different combinations to see whether the 9 combinations, each of them is belonging to my family of transfer functions or not. So let's start from, let's say, the first combination. So f is 1 and let's say g is 2. So 1 basically says that if x equals top, then top LC. So I'm writing 1 here. And now it's getting composed with 2. So I first apply 1 and then I apply 2. So let's say the first, if the input was x, if I apply 1, then this is what I get, this expression that's shown here. And then whatever is the return value from this function, I apply 2 on it, which basically means that I apply 2 on it. And so this whole value gets checked against top. And if the answer is true, then the return value is top, otherwise it's bottom, because that's the second transfer function that we have. Now this is the transfer function that we obtain by composing 1 and 2. And if I just simplify it slightly, then I can see that this thing in the brackets, this expression in the brackets, actually just evaluates to x equals top, because this purple expression will be equal to top if and only if x was equal to top, otherwise it will be c. And so this whole expression actually simplifies to x equals top, and that actually is nothing but now it becomes x equals top, then top, otherwise bottom, which actually looks exactly like the second transfer function. And so indeed that is just the second transfer functions, because just x equals top, then give me top, otherwise give me bottom. And so 1 composed with 2 actually gives me 2, and so here this check passes, and so we kind of check all the other possibilities. So 1 composed with 2 is 2. Similarly, you can check for yourself that 2 composed with 1 is just 1. The same argument applies again. Also, because 3 is just an identity function, so anything composed with 3 is just going to be that. So x composed with 3 is 3. Similarly, 3 composed with x is x, where x could be 1, 2, or 3. So these two rules here actually represent 6 different rules, because you can replace x with either 1, 2, or 3, and similarly here you could replace x with 1, 2, or 3. So far we have covered 6 plus 2, 8 cases. There are a few more cases left, and those are basically these ones here. So 1 composed with 1, what happens? You can check it for yourself. That's going to give me 1, and 2 composed with 2 is also going to give me 2. And so overall, we have exhaustively checked that the composition of any pair of functions is going to give me a function which belongs to the family of functions, and so we satisfy all the 3 requirements for it to be a family of functions for the data flow analysis framework.